A method of removing carbon dioxide from a spacecraft is to allow the carbon dioxide to react with lithium hydroxide. What volume of carbon dioxide at 32.6 degrees Celsius and 735 millimeters of mercury can be removed per kilogram of lithium hydroxide? We have the balanced chemical equation of lithium hydroxide reacting with carbon dioxide to produce lithium carbonate and water. We're going to end up utilizing the ideal gas law. I'm not a big fan of writing it this way as a linear equation. I like to customize my R. But writing it this way will allow us to look just at V, P, N, and T. We're looking for V, and N is a little hidden. It's tucked away in the kilograms of lithium hydroxide. This is because we're going to involve stoichiometry. There's a 2-to-1 ratio between the lithium hydroxide and the carbon dioxide. We're going to go ahead and start with 1 kilogram of lithium hydroxide. Since we don't normally do conversions in kilograms, we're going to go ahead and move to grams. This will allow us to move to our molar conversion using the molar mass of lithium hydroxide. Once we're in moles of lithium hydroxide, we can technically move to moles of any of the other components of the balanced chemical equation. So, in every 1 kilogram, there are 1,000 grams. Kilograms is gone. Next, we can use the molar mass, which is 23.94834 grams of lithium hydroxide for every 1 mole of lithium hydroxide. Grams of lithium hydroxide will cancel. It's on top and on bottom. Now we're getting very close to having moles of our gas. In order to get moles of our gas, we will use our stoichiometric relationship of 1 carbon dioxide for every 2 lithium hydroxides. We'll go ahead and scale up to moles so that we can see moles clearly cancel. I'm going to go ahead and color code this particular one so we can see that we are getting N of our carbon dioxide. Moles of lithium hydroxide cancels out. Again, this whole thing, all of our efforts, has been to get N. We have our P, we have our T, we're looking for V, and R we will customize. Again, currently it's just sitting there as a placeholder. If we go ahead and solve for volume, volume equals N times R times T divided by P. So number of moles times temperature divided by pressure times a second set of conditions, R. We'll get those second set of conditions from the mole bridge, where we said 22.4 liters for every 1 mole at STP. Since we're not at STP, the ideal gas law will include our temperature of 23.6 degrees Celsius, but we have to convert it to Kelvin. Celsius can be negative, Celsius could be 0. That would mess up our math. So if you look at the template, I have N on top, T on top, and P on bottom. Now it's time to customize our R value. Since I know where N, T, P are from our actual data, it allows me to set up R appropriately. Again, for every 1 mole of any gas under ideal conditions, we would say that we would get 22.4 liters of space occupied at STP. Standard temperature is 273.15 Kelvin, and the standard pressure is 1 atmosphere or equivalent. We're going to go ahead and make it 760 millimeters of mercury because that's the equivalent to 1 atmosphere. We'll go ahead and solve by multiplying across the top and dividing by the product of the bottom. Notice that all of my units from R cancel out except for liters. When we solve, we get 525.5 liters of carbon dioxide that can be scrubbed by this chemical reaction system.